Hello. Today we will start discussing the concept of electric current. Now, what is a current? A current occurs when something flows. In electricity, what is flowing, or the flow of what will give us an electric current? Well, obviously, it is the flow of electric charges. Now, from the understanding you have previously, what will make an electric charge move? We have said in the past that an electric charge placed in an electric field will move. Do you remember the direction of motion of an electric charge? A positive charge will move in the direction of the electric field. In other words, a positive charge will move from a high potential to a low potential. A negative charge moves in the opposite direction. The direction of motion of an electric charge, of a negative charge, is opposite to the direction of the electric field. From a low potential to a high potential. Alright, so an electric current is produced by setting electric charges in motion. So we will start by discussing motion of electric charges. You have seen earlier that a charge placed in an electric field will experience a force and move in the direction of decreasing potential. A positive test charge will move in the direction of decreasing potential. A positive charge moves from a high potential point to a low potential point, and a negative charge will move from a low potential point to a high potential point. Now remember, motion is not associated with positive charges. So motion occurs only for negative charges. Although our test charge is a positive charge, the actual motion happens with a negative charge. And so, hypothetically, we will be talking about the motion of positive charges, although actually what happens is negative charges are moving. If a negatively charged plate is connected to a positively charged plate by a conducting wire, an electric field is propagated through the wire, and the free charges in it will move because of the force they experience in the electric field. Now let's look at this diagram. Here we have a positively charged conductor and a negatively charged conductor. A positively charged conductor is at a high potential. A negatively charged conductor is at a low potential. If you now connect these two by means of a conducting wire, now a conducting wire means a conductor will allow free charges to move in it. Now what happens is, the moment the connection is established, an electric field is established inside that connecting conductor. And the electric field inside that conductor will set the negative charges to drift from the negative towards the positive. In other words, the negative charges will drift from a low potential region to a high potential region. Now what you have here is an electric current. An electric current is produced by setting electric charges in motion. Now, although, I want you to watch this carefully, although the motion is associated with the negative charges, what are moving here actually? Negative charges are moving. If negative charges are moving from the negative potential to the positive, it is equivalent to positive charges moving from the high potential to the low potential. Now, the direction of an electric field is the direction in which a positive test charge would move. And therefore, we would say, although the electric current is caused by the drift of negative charges, the electric current actually exists in the opposite direction, which is the direction in which a unit positive test charge would move. We'll talk about that in detail as we move on. Now, this is the direction of the electric field that is set up inside the conductor. And the negative charges move opposite to the direction of the electric field. Now, since the free charges are electrons, the electrons in the conducting wire will drift from the negative end to the positive end. They really don't move very fast. They simply drift from the negative end to the positive end. While the direction of the flow of these electric charges is from the negative to the positive, the direction of the electric field is from the positive to the negative. You've got to watch that. The direction of the field is from the positive to the negative, and the direction of motion of the negative charges is from the negative to the positive. There you are. The green arrow represents the direction of motion of the negative charges. That is the electron drift. Now, the drift of electrons in this way, caused by a potential difference between the two plates, is called an electric current. So, electric current is constituted by the flow of electric charges. Alright. The electric field propagates through the wire almost instantaneously. The electric field does not take a long time to propagate through the wire. It happens almost instantaneously at the speed of light as soon as the connection is established, and the electrons through the length of the wire begins to drift from the negative plate to the positive plate. Now, I can actually create that here for you. Now, I can generate Now here I have a metal electrode. I'm going to dip it into a chemical solution. It's actually dilute sulfuric acid. And another electrode which is zinc. And when I dip it in there, see what happens to the pointer of the meter. Can you see that? Well, let me take that away from there. Give me a second. Well, watch the pointer of the meter when I do this. Now, what the motion of the pointer indicates is the flow of electric current. Now, what happened is, when I dipped these electrodes in dilute sulfuric acid, the chemical action between the electrodes and the solution established positive charges on the copper and negative charges on the zinc. Now, when they are connected by means of this conducting wire, what happens? An electric field got established inside the conducting wire, and the electric field made the electric charges to drift, the negative charges to drift from the negative end to the positive end, making a current to flow. Alright, let's now look at that again. Now here I have another illustration. This is a battery. What I showed you just now is actually the principle of a battery. A battery is a device which builds and maintains a potential difference between two electrodes, between two metal plates. Now here, there is a positive metal plate and a negative metal plate. the chemical action inside the battery builds and maintains a potential difference between the positive and the negative. And you can see when the connection is established between the positive and negative through this electric bulb, what happens? An electric field is propagated through the length of the wire. The electric field is from the positive to the negative. That makes negative charges to drift. Now here what you're seeing is the drift of negative charges. So negative charges drift from the negative to the positive. Now that is the direction of the drift of electrons. Alright? And that is opposite to the direction of the electric field. Alright, so electric current in a conductor is defined as the rate of flow of charge. An electric current is caused by the flow of electric charges, and it is measured as the rate of flow of charge. Now, an electric current is represented by the letter I. We will from now on use the uppercase I to represent an electric current. So, if a charge delta Q crosses a section of the conductor in a time delta T, then what will be the definition of current? Current is the rate of flow of charge. So, I will be delta Q divided by delta T. Now, this is the basic definition of electric current. Electric current I equal to delta Q divided by delta T, the rate of flow of charge. Now, who can tell me the unit of measuring current? Now, what is the unit for measuring electric charge? It's a coulomb. What's the unit for measuring time? It's a second. Therefore, current will be measured in a unit called coulombs per second. So current is measured in the unit coulombs per second, and it is called the ampere. The unit of current is the ampere, and we will represent it by uppercase A. Now, an ampere is 1 coulomb per second. 1 coulomb per second is 1 ampere. Okay. Now we will look at what is the meaning of conventional current. You see, the electric current is formed by the flow of negative charges from low potential to high potential. But our test charge is a positive charge. Therefore, we are forced now to define the direction of current as the direction in which a positive charge would move. And that is the direction of the electric field. So, although electric current constitutes the drift of negative charges from the negative end to the positive end of the circuit, the conventional direction of current is the direction of motion of the positive test charge. And that is from the positive end to the negative end. The conventional direction of current is the direction of the electric field. Alright, let's see if we can see an understanding of this conventional direction. Let's now look at the difference between the direction of drift of electric charges and the direction of conventional current. What you see here is the direction of drift of negative charges from the positive end of the battery to the negative end. You know that a battery is represented by a short, thick line, which is the negative end, and a long, thin line that is the positive end. So, in the outside conductor, the negative charges flows from the negative end to the positive end. Now, what is the direction of the conventional current? Let's have a look at the direction of the conventional current. Now, the direction of the conventional current is from the positive to the negative. Alright, so do not confuse here. The direction of the conventional current is the direction of motion of the positive test charge, or it is the direction of the electric field. Okay, now that you know what a conventional current is, let's now continue our study of electric current. Now here I have an illustration of a battery. That's the positive end, and that's the negative end. Now when you connect the negative to the positive, here I have a bulb connected to the positive. You can see that's the direction of the conventional current. The conventional current flows from positive of the cell to the negative. So all our calculations and representations from now on will be using the conventional current, the direction of the conventional current from positive to negative. Now, an electric current can only flow in a closed path. If the path where the electric current is flowing is broken somewhere, electric current will cease to flow. Now, if the closed path is broken, then the current will stop. An electric circuit can be established by connecting a conductor across a battery. Now, this is an example of an electric circuit. This is an electric circuit. You have a battery and a conductor is connected across the battery. What does that mean? It means the conductor starts from the positive and ends at the negative so that a current can flow in a closed path. Now remember, the current flows from positive to negative outside the battery, and then it flows from negative to positive inside the battery. That is the closed path. The path of the electric current cannot be broken. It flows from positive to negative through the outside conductor, and then negative to positive inside the conductor, so that the path is a closed path. If you now make a break anywhere, the current will stop. Alright. The battery establishes a potential difference between the ends of the conductor. You see, that is the purpose of the battery. What does the battery do? Here you have one end of the conductor and the other end is connected to the negative. When you connect a conductor across a cell, the battery will establish a potential difference between the ends of the conductor. So this end of the conductor is at a high potential and this end of the conductor will be at a low potential. So negative charges will drift from the low potential to the high potential, and the conventional current will flow from the positive high potential to the low potential. Alright, let's now talk about Ohm's law. Ohm's law gives us an indication of how current flowing in a conductor depends on some of the properties of that conductor. The rate at which electric charges drift through a conductor, that is I, the current. The rate at which electric charges drift through a conductor is the current. Is that right? So the current in a conductor depends on the potential difference V. Well, that's understandable. Just the same way, the rate of flow of water. If you have a pipe that is inclined almost vertical, the flow of water through that pipe will be very fast. The flow rate will be very high. On the other hand, if you decrease the inclination, the flow rate will decrease. Now what does what does the inclination of the pipe to do with the flow rate? Well, you have flow from a high potential point to a low potential point. The flow rate depends on the potential difference. If you increase the potential difference, the flow rate will increase. In the same way, in electricity, if you increase the potential difference, the rate of flow of charge will also increase. In fact, a statement of the relation between the rate of flow of charges or the current in a conductor related to the potential difference between its ends is what we call Ohm's law. So what does Ohm's law give you? Ohm's law gives you a relation between current flowing in a conductor and the potential difference between its ends. If I want to make a current to flow in this conductor, I need to apply a potential difference between its ends. When I apply a potential difference between its ends, a current will flow in here. And how will I apply a potential difference? Well, you know that a battery, here I have a battery. All I need to do is connect a battery across that conductor. Now here, this is the positive end of the battery. I have the positive end of the battery, connect, and the negative end of the battery. What I have achieved here is by connecting a battery across this conductor, I have established a potential difference between the ends of the conductor. And that potential difference will make a current flow in this conductor. And Ohm's law gives us a relationship between potential difference and current in a conductor. Now that means greater the potential difference, greater will be the current through the conductor. Now the relation between the current and potential difference is given by the Ohm's law. So what does Ohm's law say? Ohm's law says for most conducting materials, the potential drop between its ends is proportional to the current in it. If you want to increase the current in a conductor, you increase the potential difference between its ends. So increasing the potential difference between the ends of a conductor will increase the current flowing in it. How do we write that using symbols? The potential drop between the ends of a conductor is proportional to the current. We say V is proportional to I, and always the proportionality sign can be replaced by an equal sign adding a constant. V equal to Ri, where R is a constant for a given conductor, and this R is called the resistance of the conductor. Well, any conductor will offer a resistance for the flow of current, and R is a measure of that resistance. So V equal to Ri, R is a constant and is called the resistance of the conductor. And I can write R therefore equal to V divided by I. R equal to V divided by I. What is the unit for measuring resistance? Anybody tell me what is the unit for measuring resistance? What is the unit for measuring volt? Well, volt is measured, well, potential difference is measured in volt. And a volt is a joule per coulomb. Potential difference between the ends of a conductor is 1 volt, means that for every coulomb of charge that moves from one end to the other, the work done is 1 joule. That's the meaning potential difference is 1 volt. So, Potential difference is measured in volt, which is joule per coulomb, and the current is measured in coulombs per second or ampere. So what is the unit of measuring resistance? Resistance will be measured in volt per ampere. Volt per ampere, and is called the ohm. We represent it by the uppercase omega, Greek letter omega, and that is the representation of resistance. Now 1 ohm, tell me, what is the definition of 1 ohm? 1 ohm is the resistance of that conductor which when it has a potential difference of 1 volt, it will have a current of 1 ampere flowing in it. In other words, if I have a potential difference of 1 volt across this conductor, and if that 1 volt will make a current of 1 ampere flow in this conductor, then the resistance of this conductor is 1 ohm. That is the definition of an ohm. A resistor, what is the meaning of a resistor? Any conductor which offers a resistance for the flow of current is called a resistor. So this conductor can be called a resistor. And in electrical circuit, resistors play a great role. So a resistor is represented by the symbol. We will represent a resistor by this symbol. Or a conductor. A resistor is a conductor. So when you want to represent a resistor in an electrical circuit, we will represent it by this symbol. Now the green lines are the connecting leads. Now for example, I have a conductor here. Now this is actually a coil of wire. A coil of wire is wound on a frame, and I have 2 ends where I can connect these leads. For example, now watch this. I'm connecting this to a connecting lead and another connecting lead, and I can now connect this to a battery. These 2 ends, if I connect to a battery, I have an electric circuit which allows a current to flow in this conductor. Alright. Now here I have an electrical circuit. This is a battery, and this battery supplies 36 volts. In other words, if I can put a conductor here. Now remember, these yellow lines are connecting leads. Now connecting leads like this, these are connecting leads, and we would assume that these connecting leads have no resistance. They offer no resistance at all. I can pick, look at these resistors there. I have a 1 ohm, a 2 ohm, a 4 ohm, an 8 ohm, a 16 ohm. They are available. I can take any of those and put it in this circuit. Well, let me take one of them and put it in the circuit. I'm going to take a 16 ohm and put it in the circuit. That means the battery has now established what is the potential difference the battery is going to provide? 36 volts. It means the battery has now established a potential difference of 36 volts across this conductor or this resistor. What does that mean to you when we say the potential difference between the ends of the conductor is 36 volts? It means in order to drive 1 coulomb of charge from one end to the other, 36 joules of energy is spent. Alright, now do you remember the Ohm's law equation we had derived? The Ohm's law equation is, alright, tell me what it is V equal to Ri. Now what we have in here is we have the V, the voltage is 36, we have the resistor value is 16. So can you calculate the current from here? Current I equal to V over R, and that gives me V equal to 36 volts, and the resistance is 16, and that will be about 2.25 ampere. Is that right? That will be the current that will flow in the circuit, and this bulb will blow if there is more than 3 ampere flowing in it. When I make the switch fall, you see now the connection is not complete. You can see the yellow lines are not touching. So there is a break in the circuit, current does not flow. In order to make current flow, I close the circuit. Let me close the circuit and see what happens. Well, close the circuit, there you are, and the circuit stays, the bulb is okay. On the other hand, I'm going to change the battery, I'm going to change the resistor. Instead of 16, I'm going to put a 4. Let's see what happens. If I take away that 16 ohm, there you can see there. If I put a 4 ohm there, now tell me what is the current that is going to flow onto that bulb when I turn the switch on. The potential difference is 36 volts, the resistance is 4 ohms, the current will be 36 divided by 4, 9 ampere. Will the bulb take that much of current? See what happens when there you are, the bulb is gone. Now you can actually play with this. I have provided this website for you. You can actually use several values of the potential difference. You can use 18 ohms, 36 ohms, 54 ohms, or 72, these are volts, 54 volts, 72 volts, and so on. And calculate the current each time. Alright, let's move on. Now, the current I in a conductor is measured using an ammeter. Now, how does an ammeter look? Now, here is how a meter, this is actually a voltmeter used to measure potential difference. And this is what we use in the lab to measure potential difference. Now, an ammeter will also look like this. It will measure the current. So current is measured in the electrical circuit by using an ammeter. And an ammeter is connected in series with the circuit. Now look at the way we connect an ammeter. Now this is the battery. A battery has a negative end and a positive end. And how is the series connection? The positive end of the battery goes to the ammeter, and from the other end of the ammeter we come to a resistor. A resistor here is a lamp, and the connection then comes back to the negative end. You see that? This kind of a connection is called a series connection. Now, components connected one after the other in a closed path. Now that means an ammeter is always connected in series because you want to measure the current flowing in the circuit. Now, to measure the potential difference V, remember, potential difference is always between 2 points of a conductor or a resistor. So, you cannot connect a voltmeter. A voltmeter is used to measure potential difference between the ends of a conductor. And this, the one I showed you, is a voltmeter. That's a voltmeter. It says V at the center there. Okay. Now, how is a voltmeter connected? Now, in this circuit, this lamp is the resistor. In other words, what the battery does is, the battery establishes a potential difference between the ends of that lamp. And it is the potential difference between the ends of the lamp that makes the current flow in it. Now, here is the lamp. If I can maintain a potential difference between the two ends of the lamp will light up due to the current flowing in it. Now therefore, how do you connect the voltmeter? We want to measure the potential difference between the two ends of the lamp. A voltmeter is connected between the 2 points across which we want to measure the potential difference. So what's the difference between how you connect an ammeter and how you connect a voltmeter? I want to measure the potential difference between the two ends of the bulb. So I connect the voltmeter across the lamp. How do I connect it? Watch. This is my voltmeter. Look at the symbol I'm using. And I'm going to connect one end of the voltmeter to one end of the lamp and the other to the other side. So the voltmeter is connected. How? Is this a series connection? No, it is a parallel connection. A voltmeter is connected parallel to the points across which you want to measure the potential difference. So an ammeter is connected in series, there you are, and a voltmeter is connected parallel to the conductor across which you want to measure the potential difference. Or you simply connect the voltmeter between the 2 points you want to measure the potential difference. So an ammeter is connected in series and the voltmeter is connected in parallel. Let's do an example. A light bulb has a resistance of 240 ohm when operating at a voltage of 120 volts. What is the current in the filament? So, what that means is, when you establish a potential difference of 120 volts between the ends of the filament of the bulb, and the filament has a resistance of 240 ohm, a current will flow in that filament. We want to find out how much is the current. Well, we use the Ohm's law directly. We know Ohm's law says V equal to Ri, right? And we want to find I. So solve for I from there. I equal to V over R. What is the voltage? 120 volts. What is the resistance? 240 ohm. So that will be 120 volt divided by 240 ohm. That will be 0.5 ampere is the current in the filament. Another one. What is the resistance of an electric heater which takes a current of 15 ampere when connected to 120 volt supply? Now this time you know the current, you know the voltage, you need to find the potential difference. So we need to find, well, we know the potential difference, we know the current, and therefore we need the resistance. We can therefore say R equal to V over I. You see, the original Ohm's law equation is V equal to R times I. Solving that for R gives me R equal to V over I. Now use those values, 120 volts divided by 15 ampere equal to 8 ohms. Alright, another example. find the potential drop across an electric bulb. This time we are looking for the potential drop. If the filament has a resistance of 240 ohm and carries a current of 0.5 ampere. Well, we got V equal to Ri. R is 240 ohm. The current is 0.5 ampere, and therefore the voltage is 120 volts. Alright, let's now talk a little more about resistance. Now, what are the factors on which the resistance of a conductor like this depend on? Well, resistance is the resistance offered by the conductor for the drift of electric charges. What are the factors on which the resistance depend on? Can you think of some of the factors? Now, conductors that obey Ohm's law are called ohmic materials. Not all conductors obey Ohm's law, but most of the conductors that we choose to deal with will obey Ohm's law. For such materials, the resistance does not depend on the current passing through them. In other words, the resistance is not determined by the amount of current flowing in it. Resistance is determined by the physical properties of the material. For most conductors, the temperature, when current flows, we will assume that the temperature remains a constant. Most ohmic conductors, most conductors are ohmic when the temperature remains a constant. That means as long as you don't change the temperature, Ohm's law can be applied to most conductors. That's what it means. That means resistance of a conductor depends on the physical factors such as the length of the conductor, the area of cross-section of the conductor, and the temperature. These are the three things which can affect the resistance of the conductor. Tell me, if the length of the conductor increases, will it increase or decrease the resistance? Well, if the length increases, the charges have to drift through for along a long path. That means increasing the length will increase the resistance. How about the area of cross-section? Can you understand the area of cross-section? How thick is the wire? Now, if I increase the thickness, will it make easier for electric charges to drift, or will it make difficult? Well, if a lot of people are going through a corridor, a wider corridor will make it easy for the flow of people. In the same way, a thicker conductor will allow the charges to flow through it more easily. What does that mean? As the thickness of the conductor increases, its resistance will decrease. So, we can say resistance of a conductor varies directly with length. Varies directly with length means resistance will increase as the length increases. And how does the resistance vary with the area of cross-section? As the area of cross-section increases, the resistance will decrease. So let's first of all write a relation connecting length and area of cross-section. How do they affect the resistance? The resistance of a conductor is directly proportional to its length and inversely proportional to its area of cross-section. Now, can you write a mathematical relation using that? Now, it looks like this. Now, you notice here, I have replaced the proportionality sign by an equal sign adding a constant. Resistance R is directly proportional to the length and inversely proportional to the area of cross-section, or R equal to rho L over A. This is a Greek letter pronounced rho. And this rho is a constant. We call it the resistivity of the material. That means the material of the conductor it determines the value of rho. Rho is a constant for the material and is called the resistivity of the material. Alright, can you work and tell me what is the unit of resistivity? Now, to find the unit, just solve for rho. What is rho equal to? I have shown you how to solve simple equations like this. Look at this. Rho belongs to the numerator. So, that will be rho equal to RA divided by L. Alright? And unit of resistivity, if you work it out, tell me. L is in meters, A is in meters squared, and a meter and 1 meter from the denominator cancel, leaving us a meter here. And rho therefore is ohm meter. Is that right? Give me a second, I will show that to you. Now, we got rho equal to RA over L. R is measured in ohm, A is measured in meter squared, length in meter. And you see 1 meter will cancel. So, leaving a meter on the numerator and ohm also, therefore rho is measured in the unit ohm meter. Ohm meter. Now, how does the resistance depend on temperature? Temperature dependence of resistance. As the temperature increases, tell me, if you increase the temperature of this conductor, will its resistance increase or decrease? What happens is, when you heat an object, the molecules, the atoms and molecules will move at random with larger amplitude, and that will make it difficult for electric charges to drift through them. Is that right? That means if you increase the temperature, the resistance also will increase. Conversely, if you decrease the temperature, the atoms and molecules will get a lot more orderly, and that will make it a lot easier for electric charges to drift through them. So a lower temperature will decrease the resistance. In fact, at least some of you must have heard about superconductivity. The superconductivity is a particular property by which a substance loses all its resistance. Then electric current will flow in it with much ease. That is superconductivity. And superconductivity is obtained at very low temperatures. So if you lower the temperature, the resistance will become very small. You can achieve superconductivity. If you increase the temperature, the resistance will increase, and it will be difficult for current to flow at higher temperature. So an increase in temperature results in an increase in the resistance of the conductor. Conversely, a decrease in temperature results in a decrease in resistivity or resistance of the conductor. The temperature dependence of resistivity is nearly linear for all metals except at very low temperatures. The relationship is linear. Now, the resistivity of a material at any given temperature is usually compared with its resistivity at 20 degrees Celsius. Now, 20 degrees Celsius is generally understood to be the room temperature. That's why that 20. So, resistivity of any material at any temperature is compared to resistivity of that material at 20 degrees Celsius by this equation. Now, look at that equation. Rho at any temperature equal to rho 20. In other words, resistivity at 20 degrees times 1 plus alpha T minus 20, where alpha is a constant called temperature coefficient of resistivity. Temperature coefficient of resistivity. Now, if you remember the equations we use for linear expansivity, These equations are very similar to that, because the relation here, this equation assumes that the resistivity is linear with temperature. The increase in resistance is linear with temperature. You can also write this equation replacing rho by the resistance R. Look at this. R equal to R20. Resistance at any temperature is R. R20 is the resistance at 20 degrees Celsius times 1 plus alpha T minus 20. This is the change in temperature. Keep track of these formulae, where alpha is the temperature coefficient of resistance. So alpha is a constant called the temperature coefficient of resistance, or temperature coefficient of resistivity of the material. And I'm going to give you a table of values for the alpha value. Now for aluminum, I have the values of the resistivity and the temperature coefficient of resistivity. So once you keep track of these values, you can use them for solving problems. We may need them for solving problems. So you have the values of resistivity in ohm meter and the temperature coefficient of resistivity in per Kelvin. Just the same as the linear expansivity of materials that we discussed earlier. Okay, let's do a problem. A resistor constructed of nichrome wire has a cross-sectional area of 2.4 millimeters square. When a potential difference of 12 volt is applied to the ends of the resistor, a current of 0.0056 ampere exists in the resistor. What is the resistance of the resistor? What is the length of the resistor? Well, if you pick the data, you will see immediately we have enough information to find the resistance. Because if you know your Ohm's law, in order to find the resistance of a conductor, you need only the potential difference across it and the current in it. We have the potential difference, we have the current, therefore we can find the resistance. So, let's write the data. The area of cross-section of the conductor A is 2.4 times 10 to the negative 6 meters squared. 2.4 millimeters squared converted to meters squared multiplied by 10 to the power of negative 6. I hope you know that. We have the potential difference is 12 volt. The current in the conductor is 0.0056 ampere. Tell me, how do we find the resistance of the conductor? And also, I picked one more that is not given here. That is the resistivity of the material. What is the material? Nichrome. And the resistivity of that material I picked from the table is 100 times 10 to the negative 8 ohm meter. Well, resistance is voltage divided by the current, and the potential difference is 12 volt. The current is 0.0056 ampere, and that gives you 2142.9 ohms. That is the resistance of that nichrome wire. B, what do you want? What is the length of the resistor? Well, obviously we need to find an equation that contains length. And what else? We know the resistance. We know the area of cross-section. Alright, can you look for the equation? The equation is, alright, resistance equal to rho times L over A. R equal to rho times L over A. And solve for L from here. Can you solve for L from here? How do you solve for L? L equal to R times A divided by rho. You must learn to solve equations that quickly. If R equal to rho L over A, remember that rho belongs to the numerator. So L equal to R times A divided by rho. We know all those values. Put those values in there. Resistance we know. Area of cross section we know. Rho value you know. And that is 5,143 meter is the length of that wire. You can see its resistance is a very high value. And that means its length is very long. Another question. A wire with a resistance of R is stretched to twice its original length. What is the resistance of the new wire? Well, let L be the length and A1 be the area of cross section of the original wire. Therefore, what is the volume of that wire? The volume of the wire, see if this is the wire, you got the length, you got the area of cross section. If you multiply the area of cross section by the length, you get the volume of the wire. So here, volume of the wire V equal to A1 times L, and after stretching, its length becomes 2L. So I have a wire like this, which is now going to be stretched to twice its length. So now the length is 2L, and when the length becomes 2L, the area of cross section is now less. Let that area of cross section be A2. Now, will the volume change? Because of the stretch, does the total volume change? No. What is the new volume? The new volume is 2L times A2. The new volume is A2 times 2L. But this volume is the same as the old volume. Simply by stretching, you don't change the volume. So, we say we can equate the two. A1 times L equal to 2 times A2 times L. Now you can see L and L from either side cancels. We get therefore A1 over A2 equal to 2. That means the area of cross section originally is A1. Area of cross section after stretching is A2. That A1 over A2 equal to 2. We are now going to use that to find the resistance of the conductor. Before stretching, its resistance is R. Can you write an equation for R before stretching? R equal to rho L over A. There you are. Rho L over A. And solve for L from there. L equal to R A1 divided by rho. Alright. After stretching, its resistance R prime. I just wrote R and put a prime and call it R prime. And that is the resistance after stretching. Can you write an equation for that? R prime equal to rho times 2L over A2. Well, solve for L from, now this L, what is this L equal to? You can see I'm going to replace that L by R A1 over rho. So that will be rho times 2, that L becomes now R A1 over rho, and of course that A2 is there. What all I did is replace that L by R A1 over rho. Now what happens? You can see rho and rho goes, and A1 over A2, you see this A1 over A2 is 2. I can replace A1 over A2 by 2. And what does that therefore give you? That will be 2R, after I cancel rho and rho, it will be 2R A1 over A2. But A1 over A2 is 2. Therefore, the resistance after stretching R prime is 2R times 2 is 4R. So, when you stretch the wire to twice its original length, its resistance became 4 times the original value. And that has been a good problem, and you should be able to do problems of this type. I will get back to you with the second part of this lesson later on.